Okay, so hello and welcome to another live stream. Today it is gonna be a short one, probably. I want to learn more about graph neural networks. Oh, wait a second. I want to learn more about graph neural networks, and I think there is a lot of literature on this. I have searched for papers we can start with, and the first paper we are going to look at is the paper is my OBS gone? Where is it? OBS is gone. Here it is. Yeah. So the paper we are going to look at is one of the papers that is part of the reading list of Ilya Sutskever. That he wrote for John Carmack, and I think it may be a good starting point. I don't know. Maybe I don't have enough background to read this, but we're gonna see. We're going to start with reading the abstract, reading the introduction, taking some notes, and reading the structure of the paper. And then we're probably going to read the result, maybe the conclusion and future work. And then we're maybe doing a second pass over it. So first we are trying to understand what this paper is actually saying, what they're doing. I already had a glimpse at it, but we're going to see what it does. Because on the one hand, it, I think, tries to summarize the literature on graph neural networks into a single framework they call message passing neural networks, and they use that framework on a specific application that is for some molecules. I'm no expert by any means in regard to that. So let's see how it goes. I hope that everything is working as expected. Let's test the audio for a second. Okay, I think it works. So yeah, let's get right into it. I have my Wacom tablet, and I have this app I discovered, which is Arnote, where we can upload PDFs and also have the luxury of having an infinite canvas where we can just put notes, which is really nice, I think. So all right, so neural message passing for quantum chemistry. A paper by some guys from Google Brain, Google DeepMind, and Google, yeah. And it was published in the International Conference on Machine Learning. I think this was not the only conference where it was published, but okay. So it is one of the foundational works in graph neural networks, and let's see, at least from what I understand. So let's start with the abstract. Supervised learning on molecules has incredible potential to be useful in chemistry, drug discovery, and materials science. Luckily, several promising and closely related neural network models invariant to molecular symmetries have already been described in the literature. These models learn a message passing algorithm and aggregation procedure to compute a function of their entire input graph. At this point, the next step is to find a particularly effective variant of this general approach and apply it to chemical prediction benchmarks until we either solve them or reach the limits of this approach. In this paper, we reformulate existing models into a single common framework. So this is very important, the single common framework, which is we call message passing neural networks. So this is very important. MPNNs, and explore additional novel variations within this framework. Using MPNNs, we demonstrate state-of-the-art results on an important molecular property prediction benchmark. These results are strong enough that we believe future work should focus on datasets with larger molecules or more accurate ground truth labels. Okay, so they have a dataset. So the concept of an MPNN, a message passing neural network, seems to be very important. So this is kind of an aggregate of, or a framework, which this is a little bit annoying about this tool, that I always have to click this, but yeah, so this is a framework that kind of aggregates prior work. Prior GNN work. That is what we learned from the abstract. And what we also learn is that this can be used for predicting something about molecules. Whatever that is. And they test it on a benchmark. Okay. I wonder whether there's a shortcut for this. Can I keyword shortcuts? Toggle full screen, switch to the tools, Control 6. Move view, Alt drag. Alt drag. All right, it's Alt. That's good to know. Okay, so let's start with the introduction. Introduction. The past decade has seen remarkable success in the use of deep neural networks to understand and translate natural language, generate and decode complex audio signals, and infer features from real-world images and videos. Although chemists have applied machine learning to many problems over the years, predicting the properties of molecules and materials using machine learning and especially deep learning is still in its infancy. Okay, it probably now isn't in its infancy anymore because this paper is from 2017, but okay. So I don't know anything about the state of the art, and probably we should have read a survey or a literature review on this, but yeah, let's just start with this. We want to understand this. And we will see over the course of reading this whether we need more knowledge or not, whether we need other work, whether we need some supplementary materials that explain something because we don't understand it. Yeah. To date, most research applying machine learning to chemistry tasks has revolved around feature engineering, while neural networks have been applied in a variety of situations. They've yet to become widely adopted. So when they refer to feature engineering, they mean you have a task and you want to do something, which is the tasks, and you have an expert, and that expert that knows something about the tasks, and about the input. So, well, how do we do this? So the task has an input and an expected output. And most of the times when they refer to feature engineering, they have some expert that knows this and this, and they extract information, specific information, using this expert knowledge to engineer features So in image processing, this was, for example, engineering specific filters, and then they use these features to train a model that then produces an output. The kind of lesson in the history of deep learning was that you generally don't want this expert, in most cases, to engineer specific features, because this expert might not know everything about the data and might miss some things that are actually pretty important, and these features may miss. So I think in graph neural networks there is a different kind of feature engineering, if you will, but we'll see. So, feature engineering. While neural networks have been applied in a variety of situations, they have yet to become widely adopted. Okay, this was 2017. They are pretty widely adopted now, I think. This situation is reminiscent of the state of image models before the broad adoption of convolutional neural networks, and is due in part to a dearth of empirical evidence that neural architectures with the appropriate inductive bias can be successful in this domain. So the neural network can now learn these features by itself without needing the expert to do it, like as this was done in image processing. Recently, large-scale quantum chemistry calculation and molecular dynamics simulations, coupled with advances in high-throughput experiments, have begun to generate data at an unprecedented rate. Most classical techniques do not make effective use of the larger amount of data that are now available. So, success of neural networks, or success of deep learning in general, deep learning, it always depends on data and network architecture. So the network architecture has to somehow mimic this data, but we also need quality and quantity to be able to successfully train these. Oops. So what they have, they essentially say here, okay, we have a field that generates a lot of data, but doesn't have a good network architecture that somehow resembles the data. So now we have to find an architecture that successfully can create models of the data and learn the relevant features about it. Okay, the time is ripe to apply more powerful and flexible machine learning methods to these problems, assuming we can find models with suitable inductive biases. the symmetries. So induction is you have a bunch of observations, and from these observations you then can make certain statements about these observations, which is separate from deduction, where you have statements and deduce new statements from these statements. The symmetries of atomic systems suggest neural networks that operate on graph structured data. So we now need a network architecture that can operate on graphs. How is that possible? We will see. And are invariant to graph isomorphism that operate on graph structured data and are invariant to graph isomorphism might also be appropriate for molecules. So graph isomorphism, this we have to look up what this actually means, because I don't really know what it means. I wonder if we can, what is this? Is this a selector? Yeah. So can we make this smaller? We can. Or maybe put it somewhere else because it's not really that relevant right now. The first question is, so let's keep maybe questions. What is graph isomorphism? So graph isomorphism, as far as I understand, is somehow looking at the structure. So is the structure of two graphs identical? And without looking at how do we say this without, so it is a statement about structure but not about individual nodes. So there's some aspect that says, okay, structure versus node versus actual nodes. And I think this makes statements about structure, that the structure of two graphs is the same, without the individual nodes having to be the same, and the individual vertices and edges. But okay, we'll see. So the symmetries of atomic systems suggest neural networks that operate on graph structured data and are invariant to graph isomorphism might also be appropriate for molecules. Sufficiently successful models could someday help automate challenging chemical search problems in drug discovery or material science. In this paper, our goal is to demonstrate effective machine learning models for chemical prediction problems that are capable of learning their own features from molecular graphs directly and are invariant to graph isomorphism. Yeah, so this is exactly what we said. Okay. So I think what they want to say about with this sentence here is that, okay, we have graph data, and we want an architecture that uses that graph data and that somehow processes the graph data to learn something about the data without having to have engineered features by experts. And they test it on a benchmark. And what they want is they want a specific property. They want these architectures to have a specific property they call graph isomorphism invariance. So they want the architecture to be invariant of graph isomorphism. That means I think what that means is that two graphs with the same structure are processed the same way. So they want the architecture to have, let's say we have a node in the first graph, we have vertex 1, which has an edge with vertex 2, and vertex 1 also has an edge to vertex 3. And we have also vertex 4, and they have also 2 edges. So this diamond structure. And now we have a second graph, vertex 5, vertex 10, vertex 6, vertex 9, and they have the same structure. They have the same kind of connection, but they're not the same vertices and edges. And they should be treated the same. Treated the same by the neural network architecture. And this is basic, I think this is graph isomorphism invariance. To that end, we describe a general framework for supervised learning. So we have labels on graphs called message passing neural networks that simply abstracts the commonalities between several of the most promising existing neural models for graph structured data. So there's already neural networks for graph structured data, but they want to summarize it in a common framework in order to make it easier to understand the relationships between them and come up with novel variations. Given how many researchers have published models that fit into the MPNN framework, we believe that the community should push this general approach as far as possible on practically important graph problems, and only suggest new variations that are well motivated by applications, such as the application we consider here, predicting the quantum mechanical properties of small organic molecules. See task, schematic, and figure 1. We will look at that later. In general, the search for practically effective machine learning models in a given domain proceeds through a sequence of increasingly realistic and interesting benchmarks. Here we focus on the QM9 dataset as such a benchmark. We might want to look at the QM9 dataset. QM9 dataset, which is a different paper, because I don't know this dataset. Cume-9 consists of 130,000 molecules with 13 properties. For each molecule, which are approximated by an expensive has a remark, by comparison, the inference time of the neural networks discussed in this work is 300,000 times faster. Okay, this is what they mean by expensive. By an expensive quantum mechanical simulation method, DFT, to yield 13 corresponding regression tasks. So you get the molecule with some description of their structure, and then you want to predict some properties of that molecule. In this case, 13 different properties. And the ground truth is, I think, this simulation and not the real properties, but okay. These tasks are plausibly representative of many important chemical prediction problems and are currently difficult for many existing methods. Additionally, QM9 also includes complete spatial information for the single low-energy conformation of the atoms in the molecule that was used in calculating the chemical properties. Okay, I have no idea what that means. We would have to look into the dataset a little bit more to actually understand what they're trying to do here, but I think it's not that important for now. So we already have it on the to-do list. QM9, therefore, lets us consider both the setting where the complete molecular geometry is known, atomic distances, bond angles, etc., and the setting where we need to compute properties that might still be defined in terms of the spatial positions of atoms, but where only the atom and bond information, i.e. the graph, is available as input. So there's two things, one where the complete geometry is known, the exact distances and angles, and one where the positions where only the atom and the bond information is available. In the latter case, the model must implicitly fit something about the computation used to determine a low-energy 3D conformation, and hopefully would still work in problems where it is not clear how to compute a reasonable 3D conformation, whatever a 3D conformation is. Probably where the atoms are in 3D, I would suspect. When measuring the performance of our models on QM9, there are two important benchmark error levels. The first is the estimated average error of the DFT approximation. To nature, the average error of the DFT, so the simulation to the actual nature error, which we refer to as the DFT error. The second, known as chemical accuracy, is a target error that has been established by the chemistry community. Estimates of DFT error and chemical accuracy are provided for each of the 13 targets. So I don't really know what they mean with chemical accuracy. So this is just the target DFT error. So, oops. Is the chemical accuracy the target DFT error? Who knows? One important goal of this line of research is to produce a model which can achieve chemical accuracy, probably it is, with respect to the true targets as measured by an extremely precise experiment. Okay, I suspect that data for extremely precise experiments, so that's something that in future should be something The dataset containing the true targets on all 134K molecules does not currently exist. However, the ability to fit the DFT approximation to within chemical accuracy would be an encouraging step in this direction. So they have the DFT simulation info. And they want to get into chemical accuracy with their model. But in reality, we want to have chemical accuracy on the true info, or how do we call it? The true target by experiment. So this is what we actually want. And of course, this simulation also tries to get within chemical accuracy of this. And of course, our model should be better at doing this, right? So they're kind of competing. While we now use it as a target, this could be two competing approaches. Okay. However, the ability to fit the DFT approximation to within chemical accuracy would be an encouraging step in this direction. So if we can get this to within chemical accuracy of the DFT simulation, then we can say, okay, maybe if we had the true values, we could get within chemical accuracy to the true values as well, which would have to be shown. In the rest of this paper, when we talk about chemical accuracy, we generally mean with respect to our available ground truth labels. So the available ground truth is then this. This is available. Available, while this is not available. Okay. In this paper, by exploring novel variations of models in the MPNN family, message passing neural network, we are able to both achieve a new state-of-the-art in the QM9 dataset and to predict the DFT. And to predict the DFT calculation to within chemical accuracy on all but 2 targets. Oh, interesting. In particular, we provide the following key contributions. We develop an MPNN which achieves state-of-the-art results on all 13 targets, which are the 13 properties. And predicts DFT to within chemical accuracy on 11 out of the 13 targets. Okay. We develop several different MPNNs which predict DFT to within chemical accuracy on 5 out of 13 targets, while operating on the topology of the molecule alone, with no spatial information as input. So we don't know where the atoms are, we just know the structure, and we can still get chemical accuracy in 5 targets, which is pretty interesting. We develop a general method to train MPNNs with larger node representations without a corresponding increase in computation time or memory, yielding a substantial savings over previous MPNNs for high-dimensional node representations. Okay, we'll see what that all means in the future. We believe our work is an important step towards making well-designed MPNNs the default for supervised learning on modestly sized molecules. Okay, so size of the molecules or size of the graph is probably a problem. Size of graph. Seems to be a problem. Okay, 1 second. Hey, good morning. How are you? We are reading a paper on graph neural networks. Oh, you think so? I don't know. Okay, let's continue. In order for this to happen, researchers need to perform careful empirical studies to find the proper way to use these types of models and to make any necessary improvements to them. It is not sufficient for these models to have been described in the literature if there's only... Oh, that's cool. Good to know, yeah. Sorry. Good luck with reading. Thanks. Good luck with whatever you're doing. Okay, it is not sufficient for these models to have been described in the literature if there is only limited accompanying empirical work in the chemical domain. Indeed, convolutional neural networks existed for decades before careful empirical work applying them to image classification helped them displace SVMs on top of hand-engineered features for a host of computer vision problems. So we actually have to... So only knowing that these things exist doesn't mean that they can displace the existing feature engineered things that are already there. We really have to test them and we have to measure them. So we actually have to test them. Which is kind of okay, yeah. Who would have guessed that, but okay. So the rest of the paper is structured, they not really tell that, but let's look at the structure. So here they will introduce their common framework, message passing neural networks. And they have a bunch of different architectures, probably from the literature, and they are trying to summarize them in a common framework. Moving forward, so they probably say here, okay, there are so many of different approaches. They are all kind of the same. We can summarize them, and so on. Then we have related work, which is interesting because this is also kind of related work, but okay. So this is then also about the chemical stuff. Then they introduce the QM9 dataset. Okay. Makes sense. Then they introduce variants of the MPNN. So they have message functions, virtual graph elements, whatever that means. They have readout functions, multiple towers. Okay. Then they described how they represented the input in a graph, raw distance feature, okay. Then they described their training procedure, okay. The results, which is great. One with spatial information, probably one without spatial information. And they have additional experiments. I wonder if they have actually published their source code somewhere. Oh, and they also have an appendix. Okay. Which is, okay, not that huge. Okay, let's read then the conclusion and future work. So our results show that MPNNs with the appropriate message update and output functions have a useful inductive bias, so predicting something about a population while having a bunch of observations, and then by induction telling us something about these observations, what they have in common or how they're different, learning something about that. for predicting molecular properties, outperforming several strong baselines and eliminating the need for complicated feature engineering. So this is always the thing. You don't want to have an expert engineer features. You want to have the network learn something about the data without you providing special kind of features. Moreover, our results also reveal the importance of allowing long-range interactions between nodes. Long-range interactions, okay. There's probably a bunch of hops between these nodes. So this seems to be an important thing. So long-range, they call it long-range interaction. Between nodes. So as far as I understand, which will probably be confirmed over the course of reading this, so the long range thing is, okay, we have a vertex, we have another vertex, we have another vertex, we have another vertex and another vertex, and here are also vertices everywhere, and let's say they're connected this way, or maybe, yeah, let's make it like this. And maybe it is important that vertex 1 is connected to vertex 5 through these hops. So there are 1, 2, 3, 4 hops. And what the graph neural network does is, I think, it only accumulates messages from the neighbors. So this, and this. And then in the second phase, kind of, we accumulate messages again, which then aggregate over time. And if they are very, so if the distance is very far, I think, then we have a problem with this message passing, because messages from vertex 5 might not have been here in vertex 1, or are maybe very weak. Weak, no messages at all. So, and if that is important for the task, then the network might have problems, I suspect. But this is just a hypothesis. Okay. So, moreover, our results also reveal the importance of long-range interactions between nodes in the graph with either the master node or the set-to-set output. With either the master node? Okay, I don't know what that means. Set-to-set output. Set-to-set output? What the heck does that mean? The towers variation makes these models more scalable. Okay, towers. Man, are we building cities now? Probably not. But additional improvements will be needed to scale to much larger graphs. So graph size, I put it somewhere here. Where was it? So size of the graph. This seems to be an important bottleneck. Hello. Book by the bookkeeper. Okay. So, an important future direction is to design MPNNs, message passing neural networks, that can generalize effectively to larger graphs. So size has to be a key bottleneck here. Then those appearing in the training set, or at least work with benchmarks designed to expose issues with generalization across graph sizes. Okay, it seems like the benchmark only has a specific size of graph. And yeah, they don't know whether this generalizes also to larger molecules or whether there is a problem with that. Generalizing to larger molecule sizes seems particularly challenging when using spatial information, so where the atoms are. First of all, the pairwise distance distribution depends heavily on the number of atoms. The pairwise distance distribution. Okay, this is also something I don't know. It's probably probably specific to the problem. Pairwise. What was it? Pairwise distance distribution. Question mark. The pairwise distance distribution depends heavily on the number of atoms. Second, our most successful ways of using spatial information, yeah, a 2 is probably missing here, to create a fully connected graph where the number of incoming messages also depends on the number of nodes. Most successful ways of using where the number of incoming messages also depends on the number of nodes. Okay, this also has to do something with how the network works by passing messages around between nodes or vertices. To address the second issue, we believe that adding an attention mechanism over the incoming message vectors could be an interesting direction to explore. Attention. There is a paper called Graph Attention Networks that was published at kind of the same time. Networks. Okay, but I don't know how this plays into the entire thing here, but okay. So we went through the paper. We know what it tries to do. So they're scattered around different graph neural network architectures. They try to put them together in a single common framework, which they call message passing neural networks, which operate on graph structure, which allows them to not have an expert engineer features about the data, but learn the features instead. And what they also do is they test different variants of this framework on a benchmark dataset to show that they can effectively do this on an exemplary dataset. Great. So I think we understood what they're trying to do. Of course, we don't understand the details. I think I understand what graph isomorphism is, which is that the network treats two graphs that have the same structure, but not the same vertices, the same. So what could this mean for our data set? What could this mean? Wait a second. So graph isomorphism invariance. A graph, okay, this is an AI summary, let's read it. A graph invariant is a property that, such as the number of vertices, edges, or degree sequence, that remains identical for isomorphic graphs. Sure. If two graphs differ in any invariant, they are not isomorphic, while invariants help identify non-isomorphic graphs. No known set of invariants can uniquely identify all non-isomorphic graphs. Okay, this AI summary is great. Not. Okay, while I was reading, let's really try to understand what graph isomorphism is, because I think this is this is relevant. I don't know, maybe okay, here's the definition. Let G VE, so one vertex, one edge, and G tick, or G prime, V prime, E prime, so two vertices, be two graphs. We call G and G prime isomorphic and write G equivalent G prime if there exists a bijection, so a mapping, V to V with XY element edge, phi X, phi Y element edge for all XY element, oh no, equivalent edge for all XY element vertices. Such a map phi is called an isomorphism. If G and G prime, it is called an, if G is equal to G prime, it is called an automorphism. We do not normally distinguish between isomorphic graphs. Thus, we usually write G is equal to G prime, rather than G is equivalent to G prime, probably. Speak of the complete graph on 17 vertices and so on. A map taking graphs as arguments is called a graph invariant. A map taking graphs as arguments is called a graph invariant. Okay. If it assigns equal values to isomorphic graphs. Okay. A graph invariant is a function that assigns equal values to two graphs that are isomorphic. So what I said here is probably not correct. So we have two graphs, I think. Let's see if I understand it. G1 and G, or G and G prime. G and G prime. And an invariant is a mapping. So let's call this invariant F. And F takes G prime, and it maps it to the same Y value. So F of G is equal to F of G prime. And our network basically is a function approximator, right? So our neural network, this is our neural network. And they are invariant to graph isomorphism. So this is our neural network. Now we only have to know what isomorphic is. Two graphs are isomorphic to each other so long as there is a bijection between two vertex sets. Okay. So I think this is what they mean. So let's see. So let's say we have G, and G is like so. Or maybe let's read it first. VG prime, and if that bijection also preserves edges. Explicitly, this means that if UV is an edge in G, then phi U, phi V is an edge in EG prime. One can visualize a graph isomorphism in two ways. One, start with a graph and move around vertices in whatever way you want while keeping all the edges intact. Start with a graph and move around vertices in whatever way you want while keeping all the edges intact. The result, a graph that looks different but isn't really. 2. A relabeling of the vertices of G. This produces a graph that looks the same, but vertices are called something else. Okay, this was the first thing that I was saying. Okay, if we have a graph V1, V2, V3, V4, and they're connected this way, V1, and now we have V5, V6, V7, V8. They are connected the same, and the mapping basically is, okay, V1 will be V5, V2 will be V6, V3 will be V7, and V4 will be V8. Okay? Now the first, so this is the relabeling. Oops. I think this is simple, but the first one I didn't understand. That is two graphs G and G primes, blah, blah, blah. Start with a graph and move around vertices in whatever way you want. Okay, this is probably a swapping of the nodes, I think. So if we have another one, G prime prime, which is V4, V2, V3, V1, and they're connected this way. And now this is kind of a rotation. So this is the same graph, while keeping all the action. It's essentially mapping as well. A reassignment, maybe. While keeping all the edges intact. Yeah, the edges have to stay the same, but the nodes can sort of be rearranged. Kind of, right? Okay. So what does this mean for our chemical structure? We will see. But I think this is important to understand what. So our neural network, which is a mapping function of graphs, is an invariant. And is invariant to isomorphic graphs. So two isomorphic graphs. So graphs that are not, that may have not the same vertices, but have the same structure, essentially, are processed the same way. Great. Or have the same output. Have the same output. Okay. Okay, 1 second. So let's read about the message passing neural network. Message passing neural networks. There are at least 8 notable examples of models from the literature that we can describe using our message passing neural networks MPNN framework. Okay, for simplicity, we describe MPNNs which operate on undirected graphs. So undirected graphs, the edges don't have directions. A directed graph, edges have directions. So this would be denoted something like this, or which would be unidirected or something. So if there's only one direction, then it's unidirected. If there are two, it's bidirected, I think. Let's look that up. Unidirected graph. No, it's undirected. So bidirectional Okay, undirected is bidirectional, and directed is only one direction. Okay. You can see that I have not studied mathematics. As always, take it with a grain of salt what I'm saying here, because I am by no means an expert. So for simplicity, we describe MPNNs which operate on undirected graphs. Probably you can do it with directed graphs as well. Which operate on undirected graphs G with node features XV, so the V probably stands for vertex, and edge features EVW, so the edge of two vertices. It is trivial to extend the formalism to directed multigraphs. Okay. Multigraphs probably with, so what is a multigraph? Probably with different vertex types. Multigraph. Okay, multigraph. So there can be loops, and there can also be connections, more than one connection between two nodes. Okay. The forward pass has two phases, a message passing phase and a readout phase. Okay, this is important. The message passing phase runs for runs for t time steps and is defined in terms of message functions and vertex update functions, UT. So message functions, MT, vertex update functions, UT. During the message passing phases, hidden states H at vertex at T at each node in the graph are updated based on messages M at vertex at t+1, according to this. Let's not read the formula for now. Let's quickly ban this guy. Okay, great. When the sum n of v denotes the neighbors of v in graph G. Okay? We will read through the formulas in a later stage. The readout phase computes a feature vector for the whole graph using some readout function R according to y hat R H at vertex. Yeah, not read the formulas for now. The message functions MT, vertex update functions UT, and readout function R are all learned differential functions. R operates on a set of node states and must be invariant to permutations of the node states in order for the MPNN to be invariant to graph isomorphism. In what follows, we define previous models in the literature by specifying the message function MT, vertex update function UT, and readout function R. Note, one could also learn edge features in an MPNN by introducing hidden states for all edges in the graph H sub EVWT and updating them analogously to equations 1 and 2 of the existing MPNNs. Only Cairnes et al. Has used this idea. Okay. So they explicitly also mention edge features. Let's first summarize this. Okay, we have message function. Message function. So, wait. We have a message function. And let's say MPNN. We have a vertex function. And we have a readout function. So I think this is important. Okay? What the message function does, so each node also has a node representation. Each node of vertex, they're kind of mixing these two, which they definitely can, but so UT was the vertex update function. Okay. Okay, the message function, there is a hidden state for the vertex. There is a hidden state maybe for the edges, which is kind of optional for now. Let's leave it out for now. The message function takes the hidden state of two vertices, I think, and optionally the edges. So there will be two, and it produces a message, which is obviously a vector. And the vertex function takes the hidden state of the vertex and the message and computes a new hidden state. New hidden state. What the readout function will now do is it takes all hidden states of the vertices. Oops. Boom, 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 all of them. And it applies a function and generates output. Maybe it does an aggregation, and so on. So this is, I think, this is an important thing. So the message function takes the vertex, the hidden states of all vertices in the graph. No, the message function takes, for each pair, for each connection in the graph, for each neighbor, which is kind of already in detail, right? For each neighbor, it takes of a vertex, it takes the vertex itself and its neighbor, and it computes a message. All the messages are summed up, and the sum of the messages is then used to update the vertex state. So it's kind of similar to a recurrent neural network in some sense. So and this is kind of then a loop, right? This is, as you can see, this is a loop. So the first thing, so we have H v1 1, H v2 1, H v3 1, and let's say they're connected this way: v1, v2, v3. Boom, boom, boom. Then we start with v1. V1. V1 has two neighbors, as all of them have. V1 will compute a message. So I think it's mv1 2, and it is a sum. It is the message function of h1 v1, h1 v2, plus the message of h1 v1, the node itself, and h1 v3, This will then update h2 v1 to be u, the vertex update function, of h1 v1 and the message to v1. Then we repeat this for all the vertices, and then we make a readout. So we do this, I think we do this t times, if this is correct. Yeah, we do this t times. We take htv1, we take htv2, htv3, we concatenate them, for example, or we take the average, let's say average, and then we apply an MLP or whatever. I think this will be somehow how it works. Okay. So 1 second. Okay. Yeah, at this point I will go quickly grab some water because my throat is a little bit dry, and come back. Oh. Does it not? Wait a second. Does it not really capture this? That would be too bad. It doesn't really capture the screen. No. Oh, I'm sorry. This is a failure. Oh no. Oh, what a fail. Well, now you can see what I do, right? Great. Yeah, so I'm kind of sorry that you couldn't see if you wanted to see. But now you should be able to see it. This is too bad. Okay, so I wonder why the screen capture was broken. I'm sorry. Of course, no one could see what I was doing. What I was painting here in our note. But okay. So let's go over it real quick. I wrote a lot of stuff. So not that much really, but the graph isomorphic thing invariant, so a function over the graph that takes two isomorphic graphs, so that are kind of the same in structure, and output the same value. So also f of g prime prime is equal to this because they are isomorphic. If I'm wrong, please correct me. Important thing about the message passing. So the core architecture of the graph message passing neural networks is that the MPNN has a message function. The message function takes a vertex, so the vertex is the same as the node. It takes its neighbor, it computes a message for each of its neighbor with itself, it sums all of the messages up, and it then uses this message to update the vertex with the vertex update function. And in the end, after t rollouts, we compute the readout function on the last hidden states of the vertices. Okay. And of course, each hidden state for each node is a vector of some kind of dimensionality. And in the end, we just concatenate them together, or we sum them together, or we compute the mean, or whatever. Probably they will tell us how they did it here. And then we put an MLP on it, a ReLU or whatever, and call it a day for the readout function. So message function, vertex function, readout function. Very important. Good. So I think we understood that. The message functions MT, vertex update functions UT, and readout functions R are all learned differentiable functions. So we can update with them with gradient descent. R operates on a set of node states and must be invariant to permutations of the node states in order for the MPNN to be invariant to the graph isomorphism. Yeah, so this is what we said. If we permute the node states, so have them in a different order, for example, this doesn't change the output. So if we start with H2 instead of H1, while all the edges are still the same, we cannot get a different output. So this is how they make this invariant to the graph isomorphism. In what follows, we define previous models in the literature by specifying the message function MT, vertex update function UT, and readout function R used. So this is their framework. And now they take the work of other people and they try to specify these three functions. Note, one could also learn edge features in an MPNN. So edges could also have features in a hidden state, while they don't have it here, I think. Yeah, so only this one has it, right? Let's start with the first one. So this is a convolutional neural networks for learning molecular fingerprints from 2015. This is very nice because they summarize it now. The message function used is m of the hidden state of the vertex, the hidden state of the other vertex, and the edge of these two vertices is equal to the concatenation of the vertex and the edge, where this tuple denotes a concatenation. The vertex update function is used is UT. This is a sigmoid function of OK. Let's maybe not look at the formulas for now because I think it's So the degree of a vertex. I don't even know what. So what is the degree of a vertex? This is something that we also have to ask ourselves, because I don't know this about graphs. So what is the degree? I think this we answered sort of. Like, sort of. Degree of a vertex. What is that? Let's read first. I don't know if it makes a lot of sense if we go through all of these now. I feel like it doesn't. Okay, the degree, so is a learned matrix for each time step t, and the vertex degree n r has a skip connection to all previous hidden states and is equal to f. Okay, I think it doesn't really make sense to go through all these because it's very specific. What is important? Okay, there is a message function, a vertex function, and a readout function. The message function aggregates messages on a vertex with all of the neighbor vertices. The message function is then used to update the vertex with a vertex update function. And in the end, after t time steps, we get a readout with a final regression value. For example, I don't know, I don't even know the 13 properties they were predicting here. So yeah, but we can do a regression then on a graph. Yeah, so there are various different methods. We can look into them, but I don't think it makes a lot of sense right now. There are gated graph neural networks. There are convolutional networks for learning molecular fingerprints. There are interaction networks, whatever that is, molecular graph convolutions. So they had edge features, and deep tensor neural networks. Laplacian-based methods, okay. Laplacian? I don't know. Laplace? Okay. These methods generalize the notion of the convolution operation typically applied to image datasets to an operation that operates on an arbitrary graph with a real valued... Oh. Let's not read that. Let's read the next one. Moving forward. Given how many instances of MPNNs have appeared in the literature, we should focus on pushing this general family as far as possible in specific application of substantial practical importance. This way, we can determine the most crucial implementation details and potentially reach the limits of these models to guide us towards future modeling improvements. One downside of all of these approaches is computation time. So we already discussed this. Graph size and computation time are a problem. And we should know why. And at the moment, we don't know why, really. But it's probably because we do this message passing and we do it t times. So we can do it. We then have to unroll the graph, the automatic differentiation graph, similar to what a recurrent neural network is doing. And probably this is the problem. Maybe there's also a problem where you can't really batch, but I don't know. Maybe you can also speed this up in quite a substantial way, somehow. So, is computation time. Recent work has adapted GGNN architecture. Okay, what was the GGNN architecture? So it is gated graph neural networks, okay. To larger graphs by passing messages only on subsets of the graph at each time step. So this maybe has to do something with, so computation time seems to be a problem. Computation time. Subset of graphs. Does this maybe have to do something with graph coloring? Which I don't know how that works, but it think it has to do something with splitting up the graph so that you can do parallel execution. So can we somehow parallelize this maybe? Parallelize? Question mark? Okay. By passing messages only on only subsets of the graph at each time step. In this work, we also present a MPNN modification that can improve the computational cost. I'm interested in that. Okay, so now related work. This will probably introduce, this will introduce the benchmark, the task that the benchmark is trying to do, or the tasks. And let's see, let's just read through it. We probably won't understand a whole lot because I have no background in chemistry, and yeah, I don't even know what it does. But let's see. Although in principle, so related work, although in principle quantum mechanics lets us compute the properties of molecules, the laws of physics lead to equations that are far too difficult to solve exactly. Okay, so there's something we want to compute about molecules, and there are physics that describe how these molecules behave or should behave, and we can solve them directly. We don't really need to know why, but okay. Therefore, scientists have developed a hierarchy of approximations to quantum mechanics with varying trade-offs of speed and accuracy, such as density functional theory, DFT, with a variety of functionals. The GW approximation and quantum Monte Carlo. Despite being widely used, DFT is simultaneously still too slow to be applied to large systems, scaling as O of n to the n cubed, where Ne is the number of electrons, and exhibits systematic as well as random errors relative to exact solutions to Schrödinger's equation. For example, to run the DFT calculation on a single 9 heavy atom molecule in QM9 takes around an hour on a single core of a Xeon E5, blah blah blah. Using a version of Gaussian G09, I don't know what that means. Okay. For a 17 heavy atom molecule, computation time is up to 8 hours. Empirical potentials have been developed, such as this Stillinger-Weber potential, that are fast and accurate but must be created from scratch, from first principles for every new composition of atoms. Whatever that means. So essentially, probably, this is very slow. Can we approximate this with a graph neural network? Can we just learn a function mapping on graphs that don't have to do these simulations? Hu et al. Used neural networks to approximate a particularly troublesome term in DFT called the exchange correlation potential to improve the accuracy of DFT. However, their method fails to improve upon the efficiency of DFT and relies on a large set of ad hoc atomic descriptors. Two more recent approaches by Bela and Pariniello and Rupp et al. Attempt to approximate solutions to quantum mechanics directly without appealing to DFT. In the first case, single hidden layer neural networks were used to approximate the energy and forces for configurations of a silicon melt with the goal of speeding up molecular dynamic simulations. The second paper used blah 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 to infer atomization energies over a wide range of molecules, in both cases hand-engineered features. So this is again hand-engineered features. They know something about the task, they have an expert, they engineer features, and they then put something on it like an SVM or whatever, or do a regression. The second paper used kernel-ridge regression to infer atomization energies over a wide range of molecules. In both cases, hand-engineered features were used, symmetry functions, and the Coulomb matrix, respectively, that built physical symmetries into the input representation. So they were not operating on a graph structure, but rather transforming the problem by feature engineering into something that you can put in a simple regression. And this is exactly what the authors want to overcome. They want to directly operate on the graph. Operate on the graph directly. Versus feature engineering plus simple ML. I call it simple ML. That's really a bad term, but think of a linear regression, a whatever a kernel ridge regression is, kernel ridge regression. Kernel ridge regression combines ridge regression, L2 norm regularization with a kernel trick. Okay, there's a kernel trick. It's kind of your regression with a little bit more advanced, but it's not fundamentally operating graph data, which we want to change with this work. Both of these lines of research used hand-engineered features that have intrinsic limitations. The work of Bela Pariniello used a representation that was manifestly invariant to graph isomorphism, but has difficulty when applied to systems with more than 3 species of atoms and failed to generalize to novel compositions. The representation used in RUP is not invariant to graph isomorphism. So again, invariant to graph isomorphism means you have a function or a regressor that takes in a graph or 2 graphs that are isomorphic, so kind of the same in structure, and lead to the same regressed value, which was then not the case for this approach they were using. Instead, this invariance must be learned by the downstream model through dataset augmentation. Okay, so they then generated other examples that were isomorphic, and it was not isomorphic by design. You had to augment the data. In addition to the 8 MPNNs discussed in section 2, there have been a number of other approaches to machine learning on graphical data, which take advantage of the symmetries in a number of ways. One such family of approaches define a preprocessing step which constructs a canonical graph representation which can be fed into a standard classifier. Examples in this family include blah blah blah. Finally, Scarcelli et al. Define a message passing process on graphs which is run until convergence. Instead for a finite number of times as in MPNNs. Okay, now we get to the dataset. To investigate the success of MPNNs on predicting chemical properties, we use a publicly available QM9 dataset. 1 second. Good. Molecules in the dataset consist of hydrogen, carbon, oxygen, nitrogen, and fluorine atoms and contain up to 9 heavy non-hydrogen atoms. In all, this results in about 134,000 drug-like organic molecules that span a wide range of chemistry. For each molecule, DFT is used to find a reasonably low energy structure, and hence atom positions are available. Okay. What is an energy structure? Energy structure. Atom positions are available, okay? Additionally, a wide range of interesting and fundamental chemical properties are computed. Given how fundamental some of the QM9 properties are, it is hard to believe success on more challenging It is hard to believe that success on more challenging chemical tasks will be possible if we can't make accurate statistical predictions for the properties computed in QM9. So if we can't do QM9, we failed. So QM9 as an entry-level test. If we can't pass this test, we don't have to even try harder tasks. We can group the different properties we try to predict into 4 broad categories. So again, we want to use the neural network as a mapping function that maps the graph to some property. First, we have 4 properties related to how tightly bound together the atoms in a molecule are. These measure the energy required to break up the molecule at different temperatures and pressures. These include the atomization energy at 0 Kelvin, U0 atomization energy at room temperature, and free energy of atomization. Next, there are properties related to fundamental vibrations of the molecule, including the highest fundamental vibration frequency, omega 1, and the 0-point vibrational energy. Okay, I have no idea what this is, but okay, we just want to learn what an MPNN is. Additionally, there are a number of properties that concern the states of the electrons in the molecule. They include the energy of the electron in the highest occupied molecular orbital, the energy of the lowest unoccupied molecular orbital, the lowest one, and the electron energy gap. The electron energy gap is simply the difference. Finally, there are several measures of the spatial distribution of electrons in the molecule. These include the electronic spatial extent, the norm of the dipole moment, and the norm of static polarizability. Okay, for a more detailed description of these properties, see the supplementary material. Okay, we probably go over this for now. Okay, we began our exploration of MPNNs around the GGNN, so this was the gated graph neural network model, which we believe to be a strong baseline. So this we should probably look at. Maybe look at the GGNN. We focused on trying different message functions, output functions, finding the appropriate input representation, and properly tuning hyperparameters. Oh god. Okay. For the rest of the paper, we use D to denote the dimension of the internal hidden representation of each node in the graph, and N to denote the number of nodes in the graph. Our implementation of MPNNs in general operates on directed graphs with a separate message channel for incoming and outgoing edges. So the message function probably only takes the incoming one. Oh, in which case the incoming message, MV, is a concatenation of MV in and MV out. This was also used in Lee et al. Okay, so they're concatenated. When we apply this to undirected chemical graphs, we treat the graph as directed, where each original edge becomes both an incoming and outgoing edge with the same label. Okay, if it's undirected, it's just one. It's, yeah. Note, there's nothing special about the direction of the edge. It is only relevant for parameter tying. Treating undirected graphs as directed means that the size of the message channel is 2D instead of D. Okay. This makes sense. If we have a graph with V1, V2, v3, v4. Oops. And it's undirected. It's directed. Let's say it's like this. V1 has no incoming messages. So V1 has only outgoing. 2 outgoing messages, which are then computed. And V4, for example, has only incoming messages. V3 and V2 have incoming and outgoing messages, and they are concatenated. If we have an undirected graph, there are each incoming message is also an outgoing message. I think that is clear. The input to our MPNN model is a set of feature vectors for the nodes of the graph, XV, and an adjacency matrix, A, with vector-valued entries to indicate different bonds in the molecule, as well as pairwise spatial distance between 2 atoms. So the adjacency matrix. V1, V2, V3, V4. V1, V2, V3, V4. So for this graph, we have an edge from V1 to V4. So we put a 1 here. This could also be a different value. We have an edge from V2 to V4. So there's a 1 as well. We have an edge from V1 to V3, from V1 to V3, and we have an edge from V3 to V4. Okay, we don't have an edge from V1 to V4. And we have 4 edges, so there's 1 missing. V1 to V2 is missing. And the other ones are 0. In the undirected graph, right? If it would in the directed graph, if it would be undirected, it would be also mirrored here, right? So there would also be a 1 here and here, and so here and here, and here and here. Yeah. So this is a matrix, the adjacency matrix, which tells us something about the edges. And they call it 8. With vector-valued entries to indicate different bonds in molecules. So each entry here is a vector. So this is a vector. So it's not a scalar value. We experimented as well with the message function used in the GGNN family, which assumes discrete edge labels. In which case the matrix A has entries in a discrete alphabet of size k. The initial hidden states HV0 are said to be the atom input feature vectors XV and are padded up to some larger dimension D. All of our experiments used weight tying at each time step t and a gated recurrent unit for the update function as in the GGNN family. Okay, here we see, okay, this has a recurrent neural network in it because it does this message passing over time steps. All right. Good. So, message functions. Matrix multiplication. We start with the message function used in GGNN, which is defined by the equation, which is, okay, so they multiply the adjacency matrix with the hidden state of a vertex. Oh, the adjacency entry at VW, which is a vector. To allow vector valued edge features, we propose the message function a of EVWHW, where EVW is a neural network which maps the edge vector to a D by D matrix. Okay. Why do they use a matrix? I don't know. Pair message. One property that the matrix multiplication rule has is that the message from node W to node V is a function only of the hidden state HW and the edge AEVW. In particular, it does not depend on the hidden state HVT. In theory, a network may be able to use the message channel more efficiently if the node messages are allowed to depend on both the source and destination node. Thus, we also tried using a variant on the message function as described in this work. Here the message from W to V along edge E is this. So we take the hidden state of the vertex W, the vertex V, and the edge VW, and put a neural network on it. When we apply the above message function directly to directed graphs, there are two separate functions used min and an mout. Okay, makes sense. Which function is applied to a particular edge EVW depends on the direction of that edge. Okay, makes sense. Virtual graph elements. We explored two different ways to change how the messages are passed throughout the model. The simplest modification involves adding a separate virtual edge type for pairs of nodes that are not connected. Okay, a virtual edge. I don't know what that means. This can be implemented as a data preprocessing step and allows information to travel long distances during the propagation phase. What do they mean by that? I don't know. To change how the messages are passed throughout the model involves adding a separate virtual edge type for pairs of nodes that are not connected. Okay. We also experimented with using a latent master node, which is connected to every input node. Okay, so somehow, so the network message passing through virtual node or virtual edges. This seems to be also a thing. The master node serves as a global scratch space that each node both reads from and writes to in every step of message passing. We also allow the master node to have a separate node dimension, dmaster, as well as separate weights for the internal update function. So this is just, okay, they tried it. In our case, a gauged recurrent unit. This allows information to travel long distances during the propagation phase. It also, in theory, allows additional model capacity. Example given large values of the master without a substantial hit in performance, as the complexity of the master node model is blah. Okay. Readout functions. We experimented with two readout functions. First is a readout function used in GGNN, which is defined by equation 4. Second is set-to-set model, is a set-to-set model from Vinyals et al. The set-to-set model is specifically designed to operate on sets and should have more expressive power than simply summing the final node states. Okay. So, all right. The model first applies a linear projection to each tuple, HV at the last time step concatenated with the initial features of the node, and then takes as input the set of projected tuples T. Alright, then after m steps of computation, the set-to-set model produces a graph level embedding Qt star, which is invariant to the order of the tuples T. We feed this embedding Qt star through a neural network to produce the output. So probably we have to look at this paper, set to set for graph embedding. Multiple towers. One issue with MPNNs is scalability. In particular, a single step of the message passing phase for a dense graph requires O of n squared d squared, floating point multiplications. As n or d get large, this can be computationally expensive. So this we should probably have a look at why this is the case. As n or d get large, this can be computationally expensive. To address this issue, we break the d-dimensional node embeddings HVT into k different d over k dimensional embeddings and run a propagation step on each of the k copies separately to get temporary embeddings using separate message and update functions for each copy. Okay, so they split up the embedding. So HVT gets split up. It's kind of similar to what we have in a transformer with different heads. And so this is HVT1, HVT2, HVT3. This is just slices of this initial thing. And then we pass them individually through the network. And then we combine them again into a single value, right? With G shared across, across all nodes in the graph. This mixing preserves the invariance to permutations of the nodes while allowing the different copies of the graph to communicate with each other during the propagation phase. This can be advantageous in that it allows larger hidden states for the same number of parameters, which yields a computational speedup in practice. Because we use the same function g that operates on a smaller slice, we need less parameters. So from this follows, so they apply g, and g has now less parameters. G has less parameters, which is then computationally cheaper. Okay. This blah, blah, blah. For example, when the message function is matrix multiplication, a propagation step of a single copy takes O of n squared d over k squared. Right. Time, and there are k copies. Therefore, overall time complexity is this, with some additional overhead due to the mixing network. Okay, the mixing part I didn't understand. Mixing. Okay, for k is equal to 8, blah, blah, blah. We see a factor of 2 speed up. Factor of 2 speed up. Okay. Input representation. There are a number of features available for each atom in a molecule, which capture both properties of the electrons in the atom as well as the bonds that the atom participates in. For a list of all the features, see table 1, okay? We experimented with making the hydrogen atoms explicit nodes in the graph, as opposed to simply including the count as a node feature, in which case graphs have up to 29 nodes. Note that having larger graphs significantly slows training time, in this case by a factor of roughly 10. For the adjacency matrix, there are 3 edge representations used depending on the model. Chemical graph. In the absence of distance information, adjacency matrix entries are discrete bond types, single, double, triple, or aromatic. Okay. So they use the distance information, either the distance information in the adjacency matrix, or they use the type, which can be just a learnable thing. Distance bins. The matrix multiply message function assumes discrete edge types. So to include distance information, we bin bond distances into 10 bins. The bins are obtained by uniformly they also bin them. These bins were hand chosen by looking at a histogram of all distances, okay? The adjacency matrix then has entries in an alphabet of size 14. Okay, so they have indicating bond type for bonded atoms and distance bin for atoms that are not bonded. Okay. So bonded atoms have a different representation than non-bonded atoms. Okay. Raw distance feature. When using a message function which operates on vector-valued edges, the entries of the adjacency matrix are then 5-dimensional, where the first dimension indicates the Euclidean distance between the pair of atoms, and the remaining 4 are one-hot encoding. A one-hot encoding of the bond type. Okay, training. Each model and target combination was trained using uniform random hyperparameter search with 50 trials. T was constrained to be in the range, so T was the number of message passing rounds. In practice, any T greater than 3 works. The number of set-to-set computations, M, was chosen from the range 1, All models were trained using SGD with the Atom Optimizer with batch size 20 for 3 million steps, 540 epochs. The initial learning rate was chosen uniformly between 1e-5 and 1e-4. We used a linear learning rate decay that began between 10% and 90% of the way through training, and the initial learning rate L decayed to a final learning rate L times F, using a decay factor F, a factor in the range 0.011. The QM9 dataset is 130,462 molecules in it. We randomly choose 10,000 samples for validation, 10,000 samples for testing, and use the rest for training. We use the validation set to do early stopping and model selection, and we report scores on the test set. All targets were normalized to have mean 0 and variance 1. We minimize the mean squared error between the model output and the target, although we evaluate mean absolute error. Okay, so they do scaling on the output in the train set, of course. Results. In all of our tables, we report the ratio of the mean absolute error of our models with a provided estimate of chemical accuracy for a target. Thus, any model with error ratio less than 1 has achieved chemical accuracy for that target. In the supplementary material, we list the chemical accuracy estimates for each target. These are the same estimates that were given in Faber et al. In this way, the mean absolute error of our models can be calculated as the error ratio times the chemical accuracy error ratio. Okay. Note, unless otherwise indicated, all tables display a result of models trained individually on each target. Okay, so for each of the target variables, they train a different model. They could have also done it differently, predict them all at once. We performed numerous experiments, in order to find the best possible MPNN on this dataset as well as the proper input representation. In our experiments, we found that so this is the thing, you also have to find the input representation, which also requires a little bit of feature engineering, but okay. That's okay. We found that including the complete edge feature vector, bond type, spatial distance, and treating hydrogen atoms as explicit nodes in the graph to be very important for a number of targets. Okay. We also found that training one model per target consistently outperformed jointly training on all 13 targets, which is also interesting. In some cases, the improvement was up to 40%. That's pretty crazy. Okay. Our best MPNN variant used the edge network message function. Set to set output and operating on graphs with explicit hydrogens. We are able to further improve performance on the test set by assembling the predictions of the 5 models with lowest validation error. Okay, they also assemble them. In table 2, we compare the performance of our best MPNN variant denoted with ENN S2S and the corresponding ensemble denoted with ENN S2S ensemble 5 with a previous state of the art on this dataset as reported in Faber et al. For clarity, the error ratios of the best non-ensemble models are shown in bold. This previous work performed a comparison study of several existing ML models for QM9, and we have taken care to use the same train, validation, and test split. These baselines include 5 different hand-engineered molecular representations, which then get fed through a standard off-the-shelf classifier. Okay, these input representations include the column matrix, bag of bonds, bonds angles, machine learning, extended connectivity fingerprints, and projected histograms representations. In addition to these hand-engineered features, we include 2 existing baseline MPNNs, the molecular graph convolutions model from Canis et al. And the original GGNN model trained with distance bins. Overall, our new MPNN achieves chemical accuracy on 11 out of 13 targets on state-of-the-art on all 13 targets. Training without spatial information. So this was something that I was also thinking of, because I think they get the spatial information from the simulation, right? We also experimented in the setting where spatial information is not included in the input. In general, we find that augmenting the MPNN with some means of capturing long-range interactions between nodes in the graph greatly improves performance in this setting. So this long-range distance message passing was done with the master node. Or with edges where no edges are, so virtual edges. To demonstrate this, we performed 4 experiments, one where we trained the GGNN model on the sparse graph, one where we add virtual edges, one where we add a master node, and one where we change the graph level output to a set-to-set output. The error ratios averaged across the 13 targets are shown in table 3. Overall, these 3 modifications help on all 13 targets, and the set-to-set output achieves chemical accuracy on 5 out of 13 targets. For more details, consult the supplementary material. The experiments shown, tables 3 and 4, were run with a partial charge feature as a node input. This feature is an output of the DFT calculation and thus could not be used in an applied setting. The state-of-the-art numbers we report in table 2 do not use this feature. Okay, then on the towers. Let's quickly read this also. Our original intent in developing the towers variant was to improve training time, as well as to allow the model to be trained on larger graphs. However, we also found some evidence that the multi-tower structure improves generalization performance. In table 4, we pair GGNN towers plus set-to-set output versus a baseline GGNN plus set-to-set output when distance bins are used. We do this comparison in both the joint training regime and when training one model per target. The towers model outperforms the baseline model on 12 out of 13 targets in both individual and joint target training. We believe the benefit of towers is that it resembles training an ensemble of models. Unfortunately, our attempts so far at combining towers and edge network message function have failed to further improve performance, possibly because the combination makes training more difficult. For the training details and error ratios on all targets can be found in the supplementary material. Okay. Additional experiments. In preliminary experiments, we tried disabling weight tying across different time steps. However, we found that the most effective way to increase performance was to tie the weights and use the larger hidden dimension D. Tie the weights, I don't really know what was that again? So wait time. Wait time. What was that again? I don't know. Tying the weights, was it related to the virtual edges? I don't know. We also early on found the pair message function to perform worse than the edge network function. Okay, we also have to read on that again. This included a toy pathfinding problem, which was originally designed to benefit from using pair messages. Also, when trained jointly on the 13 targets, the edge network function outperforms pair messages on 11 out of 13 targets and has an average error ratio of 1.53 compared to 3.98 for pair message. Given the difficulties with training this function, we did not pursue it further. For performance on smaller size training sets, consult the supplementary material. Okay, let's look at the tables and just see what they did, or how well they did. Okay, so these are the different targets. This is what was ENN standing for again? It was edge neural network, right? So their edge, where did they describe this? Training, no. Readout functions. I think it was in the message functions. Edge network versus pair message. Okay, so there's a difference. All right, so this is the edge network with the set-to-set output readout and the ensemble. And here are the other previous approaches. And this is, I guess, the mean absolute error. And then also, or average, now what are they reporting again? It was average error ratio, so I didn't understand that. So the ratio of the mean absolute error of our models with the provided estimate of chemical accuracy. Okay, it's a ratio. So of course, lower is better. And across the board, their model performs better. And also the ensemble performs better on all metrics, which is cool. Let's look at their supplementary material, maybe. More detailed description of the quantum properties. We don't really care about that. Chemical accuracy. Okay. Let's do a final summary. We will go to this again, and we will probably also try to implement something. I don't know if we implement it for this data set or try to re-implement this. I don't know if I will successfully be able to do this in a reasonable amount of time, but okay. So there are different graph neural networks existing before this. They put it into a common framework, message passing neural networks. They have a message function, they have a vertex update function, and they have a readout function. They use this architecture to do supervised learning, regression, classification, whatever. The message function, so we have the graph neural network is a graph invariant on isomorphic graphs. That is, it is a mapping function of graphs, and it treats isomorphic graphs as the same. So the output of two isomorphic graphs are the same. The message function goes for each node. It looks at each of the outgoing messages for each node and the incoming messages. It computes through a neural network a function that is the message. It uses this message to update its internal state, its hidden state. It does this for each vertex in the graph. It then does this t times, so kind of like a recurrent neural network. And in the end, it uses a readout function, which can be a set-to-set neural network, which we could look at as well. And then it does the regression. They have different, on this task, they use different input representations. They try different message passing functions, which use the adjacency matrix in the edge network to compute the message function. And they also use virtual graph elements. So they introduce edges where no edges were to basically shortcut communication between nodes. Or they use a master node, which is connected to every node to shortcut propagation, which is probably relevant because if you have a limited amount of steps, of message passing steps, you may not be able to go through all of the hops in the graph to compute the influence of one vertex at the outsquares of the graph to another vertex on the other edge of the graph, which might be a problem. So, but this feels like a hack to me. Essentially, this feels like a hack. They also state that one could use attention for this, so that you don't have to have these hops and only look at the neighbors, but rather look at everything. And there's also a paper on graph attention neural networks. And yeah, but this is also only the foundation. I think on the conceptual level, I understand what it does now. It is very interesting. And of course, representing the input and maybe translating your task to a graph are one of the key challenges. Yeah, so I have a bunch of other papers I want to read on graph neural networks that formalize this more, or yeah, maybe we can look at them. So it's graph isomorphic neural networks paper. So this was what was it? How powerful are graph neural networks? This was one I also wanted to read. This is a successor, so I wanted to read this first. And there's another one that also then I think it was pre-training strategies for pre-training graph neural networks, which was published even later, which then also includes edge features. So I think this is it for this paper for now. I think I got the basic ideas. Of course, we did not implement this, and I think it's also not very relevant to do it right now. Yeah, so thanks for watching. I will now unfortunately have to go, and yeah, I'll see you on the next one with the next paper.